end for connecting to a computer.
We've already sort of covered this for a bit, but I have a oscilloscope here, which it's pocket-sized and uses the laptop instead of being a dedicated device, so it's known as a virtual instrument. Now, it may not have the same bandwidth as this, but it has a programmable open source API. Oh, it's not open source, but it's a freely available API, which you can develop your own virtual instruments and basically use it however you want. So it's fairly nifty, even though it's
The logic probes display the state of a single digital logic line, where an oscilloscope would displays voltage over time. This merely tells you if the voltage is high or low at any given instant. They're very simple to build. I was giving away kits in the Hack Center a day or so ago. If you already understand how one works, you may be too advanced a student to go ahead and build one, so I ended up buying mine. But if you want to get into digital electronics, building one of these is a very good first project. A logic analyzer is like having a whole bunch of oscilloscope or a whole bunch of logic probes all together. This model is displaying a whole bunch of traces here, and it displays with time in that direction and logical state in that direction. Generally, they're multi-channel. The better the model is, the more channels it will usually have. You can build a very simple one that will hook up to the parallel port of a PC and use Linux open source software, which only does 8 channels, but at sufficient bandwidth to do things like debugging the SPI inter-chip communication protocol. I'm going to try something and see if I can't be tricky enough to show you all what this looks like.
Yep.
Maybe... Perhaps not so much. The software I'm using is called the Fabulous Logic Analyzer. There are several programs like it, both for Windows and for Linux. I have put links to them in the Hardware Lab section of the wiki if anybody wants to go check it out. The hardware required to use this software is very, very simple. It's maybe $10 American worth of parts. It can be put together in an afternoon. The downside of having this cheap hardware and free software is that the performance is not exceptional. On the parallel port, the software claims it can sample 1 million times per second, which means it's only good for about a 500 kilohertz signal. Anything faster than that will start to display aliasing, where if there was a dip in the signal, it might be missed, and between 2 samples, the software will interpolate that there was no dip in the signal.
Another thing to take note of is some of the new USB devices are actually mixed signal. They're not oscilloscopes and they're not logic analyzers, but they're both. And the value of this is it puts both signals in the same time base. And for some smaller electronics, that can be useful if you're doing frequency analysis of a, let's say, some sort of radio transceiver, and also probing pins on the other side of that chip. It can be really useful in reverse engineering some of the protocols.
Especially in mixed state devices, anything that has both analog and digital components. This particular model may not have the bandwidth to deal with something extremely fast like the GNU software radio peripheral, but something slightly slower, less powerful, it may be able to deal with quite easily. This is another USB tool called the USB with lots of E's. It does logic analysis, oscilloscope, protocol analyzer for serial protocols and inter-IC communication protocols for between individual chips on a circuit board. The problem is it costs 1,500 American dollars. You get an entire lab for that, but it's still a fairly pricey device, and it only works on Windows. There are some do-it-yourself tools available. I am somewhat slanted towards Linux tools because I run Linux on my laptops and my desktops. Exoscope is a program that allows you to display, to treat your oscilloscope or your sound card input as the data source for an oscilloscope. It has some problems with bandwidth primarily. The bandwidth of an oscilloscope is how fast or how frequently or how high frequency a signal it can handle. The sound card of a typical computer is designed for signals in the audio range, so outside of that range, it may not be very effective. We're hopefully going to be able to get a screenshot of Xoscope here. I don't have anything hooked up to the sound card, so it's not displaying anything useful, but basically, this axis is time, this axis is voltage, and it supports multiple channels. There are stereo inputs to sound cards, so obviously there's 2 channels right there. Some sound cards have multiple stereo inputs, so you can get multiple, like 4 or more channels. It usually requires some buffer hardware to protect the port against accidentally plugging it into something that's of higher voltage than the port can handle. This is a buffer that I built at home. Hold on, I'm going to bring that back up.
Yep.
Let's see here. Those are the inputs. They're BNC coaxial connectors, like would be used for a typical oscilloscope. And then the outputs from here and here go to the sound card and have trimmers on them to adjust the level. The other potential issue with using a sound card as an oscilloscope is that it tends to be AC coupled. That is, the signal is passed through a capacitor before getting to the rest of the electronics, which can be a problem if you're watching a DC signal because it tends to cause rounding on the edges of the signal. The parallel port logic analyzer already mentioned. JTAG wigglers and flash dumpers I'll be covering a little bit later.
There's many sources for cheap tools, especially whether like power tools. Harbor Freight has Dremels for $5 almost. USD, they're all made in China. They're not going to last as long as a brand name tool, but when you're building your first lab, you can't really spring to have everything at the best quality, or else you're really going to be hurting for money afterwards. Also, you can try eBay. You may find some good deals on there. A lot of things might be marked as is, but who knows?
One good example that somebody pointed out to me at camp here is a device called the Logic Dart, I believe. I'm looking at my notes as we speak. It's a 3-channel logic analyzer in a handheld unit with a digital display. And it does sports recording, zooming in and out on the signal, triggering on certain changes in the state of the wires that you're watching, and is conveniently pocket-sized. He said it comes up for around 150 euros, usually, I believe, 2 or 3 times a year. One will come up on eBay. It looked like a fantastic tool. It also supported most of the basic functions of a volt-ohm meter, so it was essentially a small hobbyist's lab in a handheld unit about that big.
Another good place.
I'm not certain that hamfests are as common in Europe as they are in America. Does anybody know what I mean by hamfest? Okay, I see 2 people in the back. A hamfest is a get-together of people who are amateur radio operators. And it's much like this, only they're more into radio and less into computers. Generally, they have a sales section, a vendor section, where people will try to get rid of their old equipment and buy new equipment. The stuff's usually used. Some of it's very weird, but it's generally, and it's an interesting place to get interesting bargains. So we have a question in the back. He's stating what hamfests are called. What was the word again? Oh, radio rallies. Okay, that sounds very similar thing, different word for it. Dumpster diving is, of course, the art of pulling old things that nobody wants anymore out of their garbage. This is actually how I got my oscilloscope, which is an HP unit with 100 megahertz bandwidth, so it's sufficient for simple microcontroller projects, but a little too slow for modern computers. Also, if you know anybody who works at a college that has an electronics lab, that can come in extremely handy. Colleges have a higher budget than the average hobbyist, and if you know somebody who works in the lab, they may be able to get you in and let you use the equipment for a few minutes. This came in very handy when I was reverse engineering the serial protocol of a magnetic card reader. Autodidacticism, sorry about the spitting, is teaching yourself. These are a couple of authors. Forrest Mims wrote books for Radio Shack, which is an American corporation similar to Conrad Electronics, only perhaps nowadays not as much focused on the hobby market. His books are compendiums of electronic circuits. So if you're looking to do a specific task, those are very useful. They're all available through Amazon.com. Just a quick search for his name will turn them up.
Another great reference book is The Art of Electronics. Now, this book has been around since before I was born. It's recently been updated, I think, within the last 5 years. And basically, it goes through from simple circuit analysis all the way through every type of component imaginable you'll find on a board, and explains exactly what it does and how you design for it. So if you're building your own robotics projects or reverse engineering a board and you look up a part and you're like, this chip is an optocoupler. What the hell does an optocoupler do? You go in the back, you look up optocouplers, and then you'll find 5 sections which explain different uses for that part.
The Art of Electronics is structured as a textbook, so if you feel like teaching yourself all of electronics, you can start with basically high school math and eventually end up being, if not an RF engineer, then able to pass as one in common society.
The other nice thing is it's very light on the math. It's not going to get you an engineering degree if you master the material in the book, but it will give you a very practical knowledge set of, it's basically where the rubber meets the road. So it's all very practical and down-to-earth type explanations of how everything's done and how to make real circuits, not theoretical ones.
Application notes are produced by the manufacturers of generally semiconductor components, but almost all components have some sort of application notes attached to them. It's basically a description of how to use the part in a circuit, which can be very useful if you want to design something simple with a core around 1 or 2 chips that you can get application notes for. Maxim Semiconductor is especially good about their application notes and gives very verbose examples containing how to do all sorts of very useful things with their ICs. Generally, the producers of the chips will give the application notes away for free as a way of promoting the use of their ICs over those of their competitors.
They're not always called application notes. Like with the Motorola and Freescale processors, you'll find a user's manual. And for an IC, that means it's a very detailed description of every memory mapped register, every pin, every possible configuration of that chip and maybe other chips in its family, how to access the memory, the timing characteristics of the buses. It's, they usually are about 500 to 600 pages long, but it's a PDF, so it's not like you have to print it. Now, embedded engineering is our next big section. I'm not sure what happened to this slide, but basically, wow. So when you're starting your own, it's not reverse engineering, but
forward engineering.
Yeah. So when you're starting a project, you've got to look at what your requirements are. And let me skip. When you're gathering requirements, some of your requirements may be cost, it may be the space, size, weight of your device. Like the weather balloon is obviously a weight-sensitive electronic device if you're hooking up to that. Things like a badge for a convention, that's going to be very cost-sensitive if you're mass-producing it. And other things, what is the basic needs that the device needs to meet? So does it need to route? Does it need to transmit wirelessly? And is it a real-time application? Does it, are there lives depending on it? If it misses deadlines for control circuitry of like an airplane, if you you've got various